Recording. Okay, folks. Today I'm going to take a crack at describing the core principles or the core elements of Zcash technology without entering too much details, and just the bare stuff that I think everyone who's involved with Zcash should know. Without further ado, let's get started. So you have a document here. I pulled the protocol documentation, which is checked in source depot, source control. It's called Zcash protocol specification. It's pretty easy to find. However, it's quite a long document. Again, it's a document I mentioned it many times. It's more than 200 pages. A lot of it is quite technical. And I think for understanding the simple stuff or the basic stuff about Zcash, you don't need to know all of that stuff. Certainly not all the details about the proving system and stuff. There are a few things in there that we're going to look into. And especially the first part is going to be interesting. So let's go back to our slide presentation and input the first slide. So first slide would be what's the goals, right? So we want to, let me see, let's say we want to understand the core, the basic fundamentals, put it this way, fundamental concepts of the concepts, right? We want to know the terminology, so things like secret key, private key, viewing key, and the nullifiers, all this stuff we should know. And then we should know about, so before that we should know about like the transactions, right? And I think terminology would be good enough. And then we can take a look at how to use the SDK, right, for making transactions and stuff. Okay, so let's go with the first thing, the fundamental concepts. First, another slide. What am I doing here? I'm bringing first another slide, right? All right. So, oopsie, this is a title guy. Just this one. Okay. Fundamentals. Let's put it this way. Fundamentals. Okay, so you assume that you already know how Bitcoin UTXO model works. So just a quick recap is that in Bitcoin and Zcash is inherited greatly from Bitcoin. You have the model where what you do is you track the transactions that track transfers of coins between parties. And so transaction is a series of inputs that consume coins, and they produce outputs, which are creation of coins. So there should be a balance between the two, and that you can't create coins out of nowhere unless we're talking about the mining transaction. So what you have is that the inputs should refer to previous outputs that were not used before. So they're called unspent transaction output, UTXOs. And the transaction outputs that you create in your transaction are going to be new unspent transaction outputs. Right, so that's fundamentally that's all you have really about that we're getting from Bitcoin. So these UTXO, so they are called nodes in Zcash. Node, they have things like they have a value, so the value of the coin that you have, and they have an address. So the address is semantically kind of identical to the key, a public key, which allows you to specify which secret key should be the signing key for spending these coins. Otherwise, the coins could be spent by anyone, right? So you have the value and you have an address. Okay, and in for the case of Zcash, shielded transactions have also a memo. So memo is simply arbitrary text or arbitrary bytes that you can associate with a node. Right. The big difference is that a node is encrypted. Right. And once it's encrypted with a mechanism which is called, I think, authenticated message encryption. So that means that you see the encrypted node, you don't know who has encrypted it. So you need to, there's no address that matches, well, there's no key that matches this particular node. There's no address that matches that particular node. So once it's encrypted, you will not see the value, the address on memo. All this stuff is gone. I mean, it's hidden. Let's say, call it hidden. So unless you have the key that allows you to decrypt, you won't know any of this stuff. Right? So that's one big part of the challenge of wallets. They have to try to decrypt everything that goes through, because they cannot see, they cannot find beforehand which transactions have nodes that they receive. They have to try everything, and it's authenticated message encryption. Not authenticated. It's probably something else. Huh? Okay, forget about that part. In the sense that if you decrypt, you would know if you were successful or not, right? So you can recognize garbage encryption from the actual proper decrypted value. So that's a small point, but it's an important point to have. So nodes are encrypted, and that's one of the main thing about Zcash, is that Zcash uses strong encryption, and there's no way. So this encryption is very standard. It's SHA-20. Has nothing to do with Zcash Dark or anything. It's very strong encryption that is used in other areas. So this is how nodes are created. So we are talking about outputs here, and then you have also inputs, right? So this is the node, which is like the output. So the outputs, and then you also have inputs. So in the context of UTXOs, of Bitcoin, the inputs are previous outputs of previous transactions that are not used before. Because Zcash don't want to let you know which nodes have been used, even though they were encrypted. They don't want to know even the transaction height or transaction ID where the node was created in here. So instead of using a reference to a previous transaction, they use nullifiers. So nullifiers is what you would have. How can I do this? Okay, nullifiers is what you would have for inputs. So nullifiers is very opaque. It's just a series of bytes that bear no particular meaning. Except that in order to create a nullifier, you need to be to have enough to be able to kind of decrypt the node. Right? So it comes from a key that you have. So we're going to talk about keys a bit later. But the main takeaway from this is that if you're not able to decrypt the node, you will not be able to generate a nullifier, right? So again, let's take this with a little bit of salt, a grain of salt, until later, where we'll clarify exactly what keys we're talking about. But for the moment, let's say that as simplification, that if you're not the account owner, if you're not the person who receives the node, you will not be able to create the matching nullifier, right? And another point important is that the nullifier that is uniquely associated with the node, right? And that's very important, because when you create a nullifier and you publish this as a transaction, if the people who receive these transactions, they would not be able to decode the nullifier. Actually, nobody really can. but they will see if that nullifier is used before. So they have to keep track of everything, every nullifier that went through the network, in order to detect double spends. So even if you yourself is the only person who is able to compute the nullifier that matches a particular on one of your node, you will not be able to create a second nullifier, because there's some pretty much a one-to-one association. And because of that property, if people keep track of every nullifier that went through, they will be able to detect double spend. So nullifier is not so complicated if we just care about this, right? So the next thing to talk about is the keys, right? We're talking about keys, and how they are used to decrypt the node and to produce the nullifiers. So keys here, there's a pretty complex relationship between keys, but most people, I mean, we reason in terms of seed, right? So we have a seed phrase. We have 24 words were randomly generated and then given to us, and we know that from that seed phrase, so it's like 24 words, we know that basically we can do everything. So a little bit on how this stuff is done is interesting. So one thing that is first we can do with the seed is to derive keep keys. So from the seed plus a path, you can get keys, or one key set of keys. So I said keys here because there are more than one key, but the main thing is that these keys are kind of all related to each other, right? So we'll see that a bit later. But the part I'm interested in here is the fact that the path allows you to create nearly an unlimited number of keys. As long as you know the path, and usually the path is public, you would be able to create keys from the seed. So you only have to keep this part secret. So this part has to be very, very secret, because this part here, this path, is a convention. So the convention is described in several zips. So zips 212. Okay, it's not 212 or 12. Okay, zip key derivation. If you can see, I didn't really prepare. 032. Okay, 032. Yeah. So this is about the specification that describes how, more details than what I'm saying, of course, right? But what is the path that is used to derive these keys, right? But the main thing here is that keep this guy secret, because the path and this algorithm to generate the keys is public. Now everybody knows, and everybody is using the same to be consistent. And that's why when you put the same seed in several different software that use the same algorithm, so whether it's Z Wallet, or whether it's Zeg Wallet, or you will have the same results. You have the same address, and you basically, that's because you get the same keys, right? So these keys that you have here, again, I say plural because it's actually a combination of stuff. Their relationship is described here. Okay, here, right? So this is this part, and you can see that the beginning is this guy, right? That's why we were saying that the this documentation, zip 32, really only leads you to the first key, right? Because that's a standard that actually comes from pretty much from Bitcoin. So it goes to one secret key, and then for that secret key, you can derive a bunch of other keys. And that is described here. All these keys are coming from that spending key. Or so they call it spending key. Let's call it spending key like them. Right. And so let's take a look. So these A key are keys for signing. And the N keys here are the keys that are used for creating the nullifiers. So you can see now that yes, they are coming from our master spending key, right? So this one here, the spending key, sometimes is described as a secret key main. You will see that when you export your secret key in a wallet, Zcash Dev will have a form that's like secret key hyphen and then a bunch of letters and digits, right? So that's the way to write out this spending key, and that's why from that spending key you can derive all this stuff. But you can see that you can only derive everything relative to one address or one main address, right? So with the seed you have much more capabilities, because the seed can derive many spending keys. So you can have a lot of different accounts that don't seem to be related from the perspective of the address, from perspective of this tree, but they come from the same seed. And that's a reminder that seed are the most important thing to save. Right? Because from the seed you can derive the spending key, and spending key can derive all the other stuff, right? But right now we are more interested with this diagram and what we have with the spending key. So we see nullifiers, right? So nullifiers, there's a combination of the nullifier secret key and this N key, which allows you to relate to a particular node and create a nullifier. So this is not a nullifier, right? Because obviously each node will have a different nullifier. But what we should know, right, is that this N key plus the node will give you the nullifier. And this guy here is for signing, so we don't really, it's not, that's all we should remember about. And we have therefore only this IVK and OVK. So IVK, may have heard of this before, is gives you the ability to decode the transactions. So when you receive a transaction, so let's go back to this document. Let's see. Alright, so the encoding is what we want, right? So payment address. Oh, here is one. So this is what you would have. It's plain text. Sorry, it's plain text. Maybe later. Yeah. Oh, cool. This is the part where I say this is really hard. I read this document many times, and I still have issues finding the information I want. Even though I know it's around here. It's a node plain text. Sprout, sapling, encoding keys, full using keys, spending keys. It's description. Description. It's actually here. So I don't know why, for some reason they put the form of the output inside the consensus changes from Bitcoin. All right. So this is what you would have in the blockchain. So this is the content in terms of actual physical content of an output in the transaction. So what you can see here is we have a proof that Zcash Dev that this stuff is actually holds true, but we can ignore that. Then we have these other parts here. We have CV, which is basically a commitment on the value. So it is a value commitment. So again, this is some kind of encoding or encryption of the hiding of the value in a way that we can still check whether the transaction uses the output is not greater than the input. So it's a smart way to ensure that that property stands, but without giving the actual value. The CMU is the node commitment. So once the node is encrypted, we have this CMU, which is going to be stored by every node participant. Every node we're gonna keep the CMU for all the nodes in order to detect spends. So, and then we have this part. Which is one part of the key to decrypt the node. Right. So somewhere there's this guy is the node encrypted, right? You can see it's the largest content, 580. And in order to decrypt that ciphertext, you need that ephemeral key plus your viewing key. Right? So this guy is public, so obviously that's not enough for you to decrypt the ciphertext, but you need that guy plus your incoming viewing key to decrypt that guy, right? So when you give your address to somebody, right, you implicitly ask him to use that address to generate an encryption key that you will be able to reverse by knowing the IVK, right? So for you, it's reversible. You can derive the encryption key used here, and obviously when the guy creates the payment to you, he knows what secret. Well, not secret, but what encryption key he has used to create this part. But if he doesn't store it, and we just see that later. So even if he himself sees this block later, and only sees ephemeral key, he will not be able to decrypt the transaction anymore, because this ephemeral key is only useful if you have the IVK. So that's the power. It's a bit non-intuitive because it uses asymmetric encryption, so public and private key encryption. So in order to kind of go around this little issue, there's a third part here, which is the ARP ciphertext. So now with your if you are somebody who makes a payment, right, and you want to decrypt the payments that you have done, because we have also this part, you will be able to do it, right? And okay, so let's do it here, right? So with so we have public keys. Well, it's not really public because you don't show it, but it's okay. So they call it viewing keys, right? So we have incoming viewing key, right? So IVK, and that guy allows you to decrypt your own node. Received nodes, right? And then you have the outgoing viewing key, OVK. And that lets you decrypt your own send nodes, right? So unless you send nodes to yourself, it's not going to be the same stuff, right? You are sending nodes to other people, so you will be able to decrypt your outgoing transactions. And you will, with the OVK and with the IVK, you can decrypt the stuff that's coming to you, right? And again, here, that's part of this. The story is here. The story is hello. Okay, the story is here. Is that from the secret key you can derive this OVK, right, which is carried on here, and from this guy here, AKNK, you can derive this guy, right? So you can see that IVK is used to derive the address, but not with the OVK, right? Actually, it's kind of logical. To receive something, you don't need to be able to send to it, right? So, and also another thing that is interesting here is that this part is actually optional. If you make a transaction and you don't want to have the ability to read it later, you can make a transaction that has a dummy OVK, right? But obviously you can't do one that has a dummy IVK. Nobody you will be able to receive it, right? So I think that actually we covered pretty much everything about keys. So that's one thing here, is that OVK optional, right? Then what else do we need to know? Right? So let's make another slide. So to summarize this stuff, when you have an account, right? What you need to know is the balance. You want to know the balance. So balance is incoming minus outgoing, right? And the incoming, you get it from the from IVK and plus scanning. So this is the part where you have to scan the blockchain, all transactions, whether it's blockchain or mempool, try to decrypt and with your IVK and see if it's yours, and then you can you have this stuff. You have the value, the address, and the memo. So you would be able to detect the incoming money, right? And the outgoing is from nullifiers. Right. So there's a trick here that's important to notice, is that if you only have IVK, you would not be able to detect this part, and these guys are very unrelated. And without detecting this part, you will obviously overestimate the balance of your account, right? So it's very important to be able to have the nullifier, and this comes from having the full viewing key. So we forgot about that. So the full viewing key, viewing key is equal to basically ability to have IVK, OVK, and NK, right? So that all this stuff together is required for getting the balance, right? So when we see when we talk about viewing key, most of the time we are talking about full viewing key, and sometimes I make the mistake of saying IVK when I actually mean full viewing key. So I actually mean all this stuff, right? When in Zcash, you export a viewing key, or in any wallet you export a viewing key, it's actually the full viewing key that you're seeing. So you will see something like I think XView, ZView. That's that guy. This thing together, right? Then if you have the okay, so you don't need all of this to make a payment, of course, right? If you want to pay somebody, you just need the address, right? So the address comes from IVK plus a diversifier. So the diversifier is something that you can fairly arbitrarily use. So not all values are possible, but lots of them are possible. So with a diversifier and IVK, you create you can infer or derive, an address, right? So this is where, and the address actually contains the diversifier, right? So so that's it for this. So I think by now you understand you should be able to read and fairly have a good grasp on the meaning of all these terms here. All right, so we can go to the next topic, and I think it's actually done. Maybe the SDK. Right, nothing much to say actually at this point about the SDK, except that if we're talking about the Libra Zcash one, it allows you to create transactions. So the biggest thing in there is the transaction builder, right? So it works with all this stuff, right? And helps you create a transaction from and create all the elements of transaction, including the Zcash doc. So it has that part, and it has a part. Okay, let's write notes about this. Russ. Right. So it has some really good stuff, right? You have things about like decrypting nodes, right, from IBK and OBK. You have something about scanning blocks. So scanning blocks means you are able to decode transactions. So I'm not saying decrypting, because decoding just means you're taking them apart. It's still going to be encrypted. Right? Just structurally speaking, you can see the elements of a transaction. What else do we have? We have the encoding and decoding of keys, addresses, etc. So this is a part where if you have a key, which is usually a binary number, or key, always a binary number, and you want to have it as a string or QR code, the library helps you transform from one string representation, textual representation, into something that is much more useful internally. So internally, it's going to be either like a point, or it's a scalar, so stuff that is related to the cryptography model. But the library helps you go back and forth between text form and that form. Okay, what else do we have in there? So maybe we should actually pull out Libra Zcash. Okay, so client backend is what we are talking about. We are talking about this stuff, right? Scanning blocks. So the stuff that a light client would need to do on the blockchain, while usually connecting to either Light Wallet D or connecting to Zcash D, right? So Zcash Client SQLite is implementation of some of the services that you need in this backend. So this implementation over SQLite. The reason here that you have this stuff is that there's a lot of state that you need to maintain. We didn't talk too in details about what kind of data you need to provide when you create a transaction, but that is not small, and that data comes from scanning the blockchain. And you obviously don't want to rescan the blockchain whenever you make a transaction. So all the data that you manage to produce, to calculate while you was synchronizing, should be stored into some database in order to speed up generation of transactions and calculation of balances. So this guy here is pretty much agnostic of the storage mechanism you use, and this one is an implementation of that storage using SQLite. Zcash extensions is, I think, about well, we don't really use it too much. It's about I think it's about transparent extensions. History, I never used this one before. I'm sorry, this is really new to me. Okay, so I don't know what that is. MMR. No, I don't know what that is. It seems to be fairly new, 4 months ago. So maybe it's related to Orchard. Okay, so you need these two guys though. Zcash primitives, they are implementation of all the things we talked about, right? We talked about, especially in sapling. So we talk about these keys, how to create transactions. This is all going to be here, right? And you have the high level objects here. So you're going to be dealing with, for example, if you're looking for IVK, hopefully it's going to be here. Yeah, this represents a viewing key. And then you can see that in the viewing key, you have an IVK. You can get the IVK out of it. Right? So I'm not going to get into too much details, but that's something that you may have to look into if you want to work in higher detail. So definitely this guy is useful, very useful. Why it's not showing anything anymore is beyond me. And then you have Zcash proof. So this is the implementation of the Zcash dark circuit to generate the proof for the transaction. So it's, I think, unlikely, less likely that you're gonna have to work with this guy here, because for Zcash the proofs are the circuits and the proofs are already established. You can't change them. So you are going to indirectly use them through the primitives, but the higher level is the transaction builder, right? So the two things I talked about is the block scanning will be here, and the decoding of transactions, the decoding of nodes will be here, and generation of nullifiers, all this stuff will be here. So these two guys are the main libraries you want to use. All right, so let's put it here. We have Zcash. So this guy is going to be in Zcash primitives, and this guy is going to be in Zcash client backend. And then you can opt to use the Zcash sorry, what was the name? Client SQLite. Right. But that's not a requirement, definitely not a requirement. And that guy, I think, is also in Zcash primitives. Okay, so that's all I wanted to say. And I hope it was helpful. And if you have questions, please comment, like, and subscribe, as they say. Until then, have a nice day. Okay, how do I stop this? Stop.